So in problem 2.8, we look at the hazard rate. Um, the exercise itself is not wildly interesting. We are given a hazard rate for a non-negative variable x. So we have a non-negative stochastic variable x. And then they say, based on this hazard rate, find the distribution function and the density, and explain why it is necessary that a is greater than 1. So given that a is greater than 1, the distribution function and the density of x may be found on page 20 in the book. So goal is to find the density and the distribution functions using lambda of x. And according to 2.9 in the book, we have that the distribution function is given by 1 minus e to the minus capital lambda of x, and the density is given by the hazard rate multiplied by e to the minus lambda of x, where this lambda of x is given by the integral from 0 to x of lambda of the hazard rate. So this is pretty much it. This is pretty much what we have to do for the exercise, and then we just need to calculate. And so the more interesting thing here is probably why is it necessary that a is greater than 1? And also, why is it even necessary for us to look at the hazard rate? So let's just take a little glimpse at hazard rates and ask ourselves, why are they necessary? So pretty quickly in the book, we kind of get the feeling of what a hazard rate is. The book tells us that we define it as a limit, right? We define it as a limit of a probability, actually, where they say define it as the limit. So consider the probability that given x is greater than some little value, then x will lie just between that little that value and a little bit farther right. Consider this probability and divide by how far away from how long this interval is. So consider this and let the length of this interval decrease towards 0. So it's a kind of immediate probability. Given that x is greater than some value, what is the immediate probability that x attains exactly that value? In the book, they call it intensity. And how do they interpret that? Well, they say if x is a lifetime, then we may interpret this thing in whole as the intensity that an individual will die at time x, given that the individual has just survived past that time. And if x is a claim, we interpret this whole thing as the intensity that the claim is exactly x, given that it is at least x. So this thing with hazard rates, why is it interesting? Well, first of all, it's interesting just because it is what it is, right? It's interesting to know what is the immediate probability of dying given you have survived past some time, for example. But then we can kind of ask ourselves, why can it be interesting in other cases? Why is it an interesting way to characterize a distribution when we have already the density and the distribution function given? So let us look at the different relations there are between the hazard rate and the density and distribution functions. So what we see in the book on the bottom of page 19 is that the hazard rate can be expressed in terms of the density divided by the survival function. Alternatively, the distribution function can be expressed in terms of the hazard rate integrated. And also the density can be expressed in terms of the hazard rate. So what do we learn from this section in the book? Well, given a hazard rate, we may find the density function and the distribution function, or the survival function for that matter. And what they actually say in the book is you can pick any kind of function to be the hazard rate, more or less. So it's not just given a specific hazard rate, it's actually given a non-negative. So we do expect the hazard rate to be non-negative. So given a non-negative function lambda, which satisfies that the integral of lambda from 0 to x, that this goes towards infinity as x goes towards infinity. So if lambda is any function that satisfies this, and if lambda is non-negative, well, then lambda defines a distribution. Then lambda is the hazard rate of a distribution. And this is one of those I am totally at a loss for words epiphany moments here, because well, why is this significant? This is extremely significant because it's nice to be able to say I can just grab any function out of thin air and it has a relation to a distribution. And it has a relation to a distribution in a way that I can intuitively understand. So this is the nice thing about hazard rates, that they actually, you can just draw up any kind of function more or less, and you can use it to characterize a distribution. What do I mean by that? Well, the thing is, why would we even want to use a hazard rate to characterize a distribution instead of a density or a distribution function? Number one, hazard rates are flexible. Unlike a density, it doesn't have to integrate to 1, so you don't need to think about that. Unlike a distribution function, it doesn't need to start around 0 and then grow up to 1. You don't have to think about that. It just needs to be non-negative. It can be increasing, it can be decreasing, it can make weird periodic swings, it can be whatever you want it to be, as long as it is non-negative. Now 2, the hazard rate is a lot more intuitive than a density. If you read the sections, if you read section 2.5 in the book, you will understand what I mean, especially in the sense that the hazard rate has a kind of relation to the mean excess functions, which in the end yields the result that if a hazard rate is increasing, then it means you can expect the mean excess to be decreasing. So lambda of x increasing has a correspondence to the mean excess decreasing. So what does this mean? It means that if we're considering a distribution where the hazard rate increases, then the mean excess, given that x exceeds something, will become smaller and smaller. So this is very well in cases where we look at lifetimes, because the mean excess lifetime becomes smaller and smaller, right? The expected number of years we expect someone to live, that decreases with age. On the other hand, if the hazard rate is decreasing, that has a direct relation to the mean excess being increasing. Now, where does that come into play? That comes into play in claims in non-life insurance, because in non-life insurance, we think about, often given a deductible D, if a claim exceeds that size, how much do we expect the claim to exceed that size by? Now, often big claims have a tendency to exceed a size even bigger, right? So this hazard function, it's extremely intuitive considered, compared to densities, where most densities just look pretty similar. They either look like this or they look something like this. And the vague differences are so hard for the eyes to spot. And the parameters are so hard for us to understand when we model. On the other hand, hazard rates are extremely intuitive, and you can just grab any function that's non-negative out of thin air, more or less, and it gives you a distribution. So that's why we like hazard rates. Okay, so I think I've spoken enough about hazard rates. I'll end this video here. Read the pages 19 and 20 just to get a better feel of hazard rates as well. And then in the next video, we will do the solution of the exercise.